Good afternoon, ladies and gentlemen. It's a great pleasure for me that I can welcome here Professor Michael Dumbser. Professor Dumbser comes from Germany. He studied in Stuttgart, where he obtained the master degree in 2001, I think, and then also a PhD degree in 2004 in the group of Professor Munz. And after that, he moved to the University of Trento, to the group of Professor Toro. And since 2018, he is professor at the University of Trento. And Professor Dumbser is well known for his contribution in computational fluid dynamics, in particular in discretizations by finite volume and discontinuous Galerkin methods of hyperbolic problems, compressible and incompressible Navier-Stokes equations. He considered also various applications, for example, in magnetohydrodynamics, and in recent years he also considered relativistic magnetohydrodynamics, which will be, I think, also a topic of this talk. So, yes, yeah, we are looking forward to your talk.
Thank you very much. Thanks a lot, Peter, for the very kind introduction, and thanks for being here and for hosting me here in Prague. It's always a great pleasure to be in Prague. It's, as I said to my friends here, yes, so there's no good reason not to come to Prague. Okay, so in recent years, we have focused our research a little bit on complicated equations like, well, Einstein-Euler equations. So if you like headaches, if you like not sleeping well, if you like to have very complicated problems and a lot of equations, if you like all this, then you may want to consider general relativity. So I will talk about DG schemes as well as finite difference and finite volume schemes for the Einstein-Euler equations of full general relativity. Okay, so basically this is the ultimate nightmare that you might consider from a PDE point of view, right? Concerning complexity, because it's a solving PDE on dynamic manifolds. Yes, that's what it actually is from a mathematical point of view. Yes, this is joint work with Olindo Zanotti and Ilya Peshkov from Trento, Elena Gaburo from Verona, and Gabriela Pupo from Roma La Sapienza. Okay, let's start. Okay, the field equations, they can actually be derived from an action principle, from a variational principle that was already found by Hilbert in the same year as the equations were published by Einstein. So this is the so-called Einstein-Hilbert action, and via the relation with respect to the metric tensor, the 4 metric, you obtain these field equations, where here this object, it looks so innocent, right? So be careful. This is the only slide where the formulas look nice. Okay, then it will get worse and worse and worse. Okay, so this object here is the 4-rigid tensor, which is a nonlinear function of the Riemann tensor. It's actually a contraction of the Riemann tensor, which is a nonlinear function of the metric tensor, sorry, and of its first and second derivatives. T mu is the so-called energy momentum tensor, from which later you can then derive the conservation laws of total energy and momentum. These equations are endowed with stationary differential constraints, which are nonlinear, and they are rather ugly. So just to give you an idea, it's well known that in the Maxwell equations, you have the condition should remain 0 for all times, because there are no magnetic moments. Yeah, so this is a simple. In these equations, I will show you later, they are in total are no numerical schemes which are exactly. And that's the Munz, if you have a stationary differential constraint. Put a time derivative in front of it, things move, because if you have an error, violated. For example, divergence of B equals violated, kind of acoustic type waves. And so something similar can be done here. So you go from 1 to 3, you can modify the Hilbert action and you add this divergence term, which formally doesn't change the action, but it changes the equations. And this Z is a vector, it's a 4-vector. Here the Greek indices, they run from 0 to 3. 0 is time and 1 to 3 are the 3 spatial coordinates. And so this Z is basically like a cleaning vector that moves the errors in the stationary differential constraints away. I will show the evolution equations later. Yeah? So here you can't see it really yet. Yeah? So then the modified field equations, so you go now from 2 to 4, the modified field equations look like this. And if Z is 0, then you still solve the original Einstein equations. But in general, your numerical method will produce errors, yes, in the constraints, and these will make Z non-zero. Here we take the classical energy momentum tensor of the relativistic Euler equations for an ideal gas. Yeah, so P is the pressure, E is the energy, and U, mu is the 4 velocity. Be careful, the 4 velocity. Velocities must be bounded by light speed. Yes, so in general relativity, nothing can move, and also special relativity, of course, nothing can move faster than light. Okay, so you have really tons of complications, right? So like in Euler equations, I mean, pressure and density must be positive. Here you have the additional constraint that velocity must be smaller than light speed. And you have the differential headaches that you have together. If you now take the 4 divergence of this set of field equations, you get the conservation laws of mass, momentum and total energy. Yes, and then there's an additional extra conservation law for the rest mass density. Now, if you start to unpack the equations, yes, because this R, I remember, is the Ricci tensor. Okay, so it's a rather complicated object. And what you now typically do is you introduce 3 spatial coordinates, a time coordinate, and you write the equations in this 3 plus 1 split. So t is time, and then you get all your spatial derivatives. Now you get the following set of equations. Gamma ij is the so-called spatial metric. So this is a 3 by 3 object. The Latin indices run from 1 to 3 only. This L beta, this is a Lie derivative on this manifold. K is basically the tensor, and this is actually the equation that contains the Einstein field equations from here, right? Yeah, but be careful, this is a second order equation in both space and time. Now you introduce an additional object to reduce these equations to first order in time. And so this is what is done here, basically. You know this usual trick from ODE as well, how to reduce a second order system to first order. And these are the evolution equations for this cleaning vector for the Z mu, right? So you basically have the time components, Z0, and the spatial components, Zi. And these guys here are actually the constraints. They are this guy, the Hamiltonian constraint, this is a scalar constraint, and these so-called momentum constraints. Be careful, R is the Ricci scalar. So this is a contraction of the Ricci tensor, which is again a nonlinear function of the metric tensor and of its first and second derivatives. And now you want to satisfy these constraints. So as I said, to my knowledge, there's no scheme that is able to preserve this exactly on the discrete level so far. Yeah. And now what we do, take these constraints and put a time derivative in front of it. Yeah. Here precisely put a Lie. Say basically Lie derivative with respect to the shift vector. Yeah, you are free to move coordinates. Yeah, in general relativity, the choice of coordinates is arbitrary. This is one of the freedom that you have in this theory. So you need to choose your coordinates. So what we do here, I will explain later. There are special choices for the so-called lapse. Alpha is the lapse, which means somehow like the second means how fast the time is passing in each point, and beta is the velocity of the coordinates, right? It's somehow like ALE in some sense. Yeah. Okay. Then, oh, now I don't know what I did. Oh, let's click here. Okay. Yeah. So now, if you look carefully at these equations, these terms here contain still second derivatives in space, right? Also here, this Ricci tensor in space contains second derivatives of the metric. And so to get rid of the second derivatives, you reduce the system to first order, which means you introduce auxiliary variables for the gradients. A, B, and D are the gradients of the lapse of the shift and of the spatial metric tensor. And now you can rewrite the whole system as a first order system in space and time. And then you can actually analyze the hyperbolicity in a proper way. Be careful. This is something is different from, say, the heat equation, right? If you have the heat equation and you say you define a new auxiliary variable, which is the spatial gradient, I don't know, of the temperature, you will not be able to write an evolution equation for the temperature in a first order form. Whereas in this system, yes. So this is somehow surprising, right? So these second order terms here, be careful, they are not dissipative. Yeah, these are not dissipative terms. This is a wave equation. Yes, written in a rather strange way. And so you can introduce gradient fields and you write down the evolution equations. And so this is how the system now looks like. The first 5 equations are now the Euler equations. So you have conservation of rest mass density, conservation of momentum, and conservation of total energy. These source terms are due to the curvature of the space-time, and they contain basically the gravitational field. Then you have evolution equations for the 4 metrics, so for the lapse, which is the rate, how fast time passes, the shift vector, and the metric tensor. Yeah, so here we use this relation for the shift. So basically, this is the so-called gamma driver. You see this here. This vector B is related to the time derivative of these contracted Christoffel symbols. It's a choice that we took from literature. It's not our invention. Then, yes, as I said, the equations get uglier and uglier. So these are the next equations. Well, the one for the extrinsic curvature and for the cleaning vector Z. Yes, so these are the main variables. So here it looks rather horrible, but it's because we needed to unpack this Ricci tensor, right? And we can write it in terms of these gradient fields A, B, and D. And these are the evolution equations for the additional gradient fields. So for the gradient of the lapse, the gradient of the shift, and the gradient of the metric tensor. You see here, there are some red terms. Yes, these red terms, they are actually 0 formally. Yes, it's like adding divergence of B equal to 0 to the equations. So why do we need to do this? You may say this is stupid. No, you add a 0 to the equations. Well, what we want is we want a hyperbolic system for which we can actually prove the hyperbolicity, which means we need to compute all our eigenvectors. You can do this. That's incredible, but I mean, these are in total 59 equations, but you can actually compute the eigenvectors. And if you do not add these terms, then your system will not be strongly hyperbolic. It will be weakly hyperbolic. So you have real eigenvalues, but not a full set of independent eigenvectors. And then if you try to apply your favorite DG scheme to this weakly hyperbolic system, then it will simply explode. Yeah, it's you do a couple of time steps, and then due to the weak hyperbolicity, you get unstable results. And it's not a problem of your method. It's a problem of how you write the equations. Yeah, so basically most of our time we spend in writing the equations properly, right? And then once you write the equations properly and once you can prove hyperbolicity, then you apply the DG scheme and then it works essentially, say, almost out of the box. Yeah, so you need to do these kind of tricks, adding these zeros. I mean, it's a little bit like adding the Godunov-Powell terms, right? The symmetrizing terms of Godunov in the case of the MHD equations, yeah, so however, here we have no symmetric hyperbolic form and no extra conservation law, right? Or no entropy, which is actually a problem, right? Also concerning nonlinear stability, we cannot say anything here. The equations in total, they are 59. Normally, state vector F is our flux tensor. B times the gradient of Q is the non-conservative stuff, and S of Q is an algebraic source term. Now we deliberately wrote the equations in the above form, and you can actually split the state vector in 3 groups. Say M is the matter part, right? That's Euler, relativistic Euler equations, and only for the Euler equations you have a conservative flux, which is what you expect because you want to solve conservation laws for the matter. Then V, this is the form metric. So the lapse, the shift, and the spatial metric tensor. So in total, there are 10 independent components. And U, dynamic variables. And now the interesting thing is, if you look at the structure of the equations, they're actually somehow block diagonal, with block rather generous. Okay, so the first block is the 5x5 Euler subsystem. And for this, everything is known, right? You know the eigenvectors and this is all fine. And the Euler equations couple to the Einstein part only via the algebraic source term, not via the differential part. Okay, so this is why you can decouple this. And in the hyperbolicity analysis, you do not need to take care of the complete system, but you can analyze the blocks separately. So matter is star. Then what you can see, you can believe me, but you can also check it again looking at the equations. These system matrices B, they actually do not depend on all the state variables, but they only depend on the metric. Yes. And then if you look at the system, the structure is such that all the eigenvectors and all the fields are linearly degenerate. Yes, all the fields are linearly degenerate. And this is what the astrophysicists also tell us, right? There are no shocks in the Einstein equations. Yes, because all the characteristic fields are linearly degenerate because the matrices B, they just depend on the geometry, let's say variables V and not on U. Okay, then there is another additional problem that I would like to mention. If you want to compute the flux for the Euler equations, you might say, well, this is easy. No, this is not easy. In relativity, it's difficult. You cannot easily express the primitive variables, velocity, density, and pressure in terms of the conservative quantities because everything is coupled via the Lorentz 1 minus v squared. And this couples all the equations and all the conservative variables with each other. Look here, right? You evolve these objects, d, say related to the mass density, si, this momentum, and e, the energy. But all the conservative variables are coupled together via the Lorentz factor in a nonlinear way. So it's not easy to recover velocity, pressure, and density. You actually need an iterative procedure. So you can boil down everything to a 2x2 nonlinear system. And if you specify your equation of state, say here in this case ideal gas equation of state, then you can reduce everything to one scalar problem in terms of v squared. But v squared is a nice quantity because you know it's between 0 and 1. Yeah, because in relativity, 1 is light speed, okay, so it's normalized, yeah, of course. So velocities in velocity squared has to be between 0 and 1. So you can use a Newton method, but if you're desperate and it doesn't use bisection, right? And if you don't find a solution, well, then it's unphysical, right? Your state variables are unphysical. But so this should not happen, yeah? Should be nice, but now if you want to study compact objects like neutron stars, you have an additional problem because these compact objects, they are embedded in water equations or rarefied gas dynamics close to vacuum. So it's really not easy to compute the variables density, velocity, and pressure close to the vacuum. So what we do is the following. Well, if the density, the variable is d, is much smaller, yes, then we set the velocity to 0, which also means, by the way, that the Lorentz factor is 1. Okay, so this is definitely not wrong. And then if d is greater than this threshold, which is close to machine precision, well, then we apply this root solver. And Good. Now we need to compute the velocity. And for computing velocity, we need to divide S, this, say, call it generalized momentum, by this quantity y, which is, where is it here? Y is here. Rho times h times w squared. Okay, so but quantity y, which can be small. And of course, the computers, they don't like division by zero. So what you need to do somehow is to filter. That's what we do. So in the absence of matter, of course, it's reasonable to believe that velocity tends to zero and not to infinity, right? Because if you divide by zero, then zero. So we just add an epsilon here, and this function actually switches off the filter if the density is large enough. Yeah, just that we don't mess up our division. This is how we do the division by zero, let's say, in the computer, because you need to do something. You have to avoid divisions by zero. So that is how our filter function actually looks like, right? So this filter, this is the quantity y here. If y tends to zero, then we force the velocity to go to zero and not to infinity, which is reasonable, I think. Okay. Now, there are several exact solutions available for the Einstein-Euler equation. Yes, so I mean, the case of black holes, for example, the Schwarzschild solution was already found 1 year after Einstein published his work. Then there is the Kerr black hole, which is a rotating black hole. There is the Tolman-Oppenheimer-Volkoff neutron star solution. So there are several solutions that are known for the Einstein field equations. And now you may want to preserve these stationary equilibrium solutions exactly at the discrete level. Yes, which means well balancing, right? So this is a concept that is well known in the context of shallow water equations, and now also in the case of Euler equations with gravity, it's extended to this more complex and ferocious PDE system like the Einstein-Euler system. So of course, I hope you all agree that the definition of a stationary solution is that the time derivative of the solution vanishes, right? So this is our equilibrium solution, QE. PDE system. Now, what we actually do here is following an idea of Berberich and Klingenberg et al., as well as Paresky and Ray, you can actually take this equilibrium PDE and subtract it from the original PDE. Yeah, so you get a difference of 2 PDE, where Q is your actual solution and QE is the known equilibrium. Be careful, it has to be known. So if you want to study small oscillations around a known equilibrium, then this is not a problem, right? It cannot be applied to general equilibria that are unknown. You need to specify the equilibrium around which you want equations. Then you simply introduce an augmented state vector, Q and QE, and you write the whole PDE as follows. It's an augmented system, right, where you have basically this triple evolution equation dt QE equal to we have subtracted the equilibrium PDE. Yeah, it means you double the variables, but you're already at 59, so going to 118 is not a problem. Yeah, and you need to have the equilibrium anyway, right? I mean, it's not that it's additional work. Yeah? If you want a well-balanced scheme, you need to know your equilibrium in each quadrature point and in each numerical flux. So in any case, you would have to store these data in your method. And now this is different from what we did previously. So in a previous work, we actually wrote our discrete solution as the exact equilibrium solution plus a piecewise polynomial perturbation around it. Yeah, where say the Q prime is the exact equilibrium. But doing this everywhere in your code is really a nightmare, right? Directly discretize this equation 41, and then it's obvious that if our discrete solution QH is equal to the discrete equilibrium, then all these terms, they will cancel out and you will get no evolution. You just have to make sure that in your numerical fluxes, you don't destroy the well balance. Yeah, here your expert. So here we have our PDE system. We write our discrete solution as a sum of some spatial basis functions by L multiplied by some degrees of freedom that depend on this time index N. And now what we like to do in Trento are fully discrete one-step schemes. So we do not integrate with Runge-Kutta in time, but we use this Ada approach of Toro and Titarev. So we actually write here everywhere also the time integrals. Now, of course, in order to do this, you need to have a time-dependent argument here. And there we have this additional discrete solution, which we call QH, which we get from a predictor, which I will show on the next slides. Yeah, so just for a moment, assume that we know this predictor. So then you get basically the update from the old time level to the new time level of all your degrees of freedom via the numerical fluxes. Be careful, these are fluctuations actually, because we have the non-conservative products. So these are actually flux differences, not fluxes. And then the smooth integral, volume integral over the smooth part. Yeah, be careful, this is something we need to do due to the presence of these non-conservative products. You cannot do integration by parts. Yeah, integration by parts, you can do it if you have a conservative problem. But for this, you basically need to interpret your solution in the frame of distributions. Actually, it's even more complicated because if B actually is able to jump now, because our DG solution is able to jump from one element to the other. Yeah, that means B of Q is actually not well defined at the interface. And on top, you have gradient of Q. So you need to give a meaning to this. And this is, I will show it on the next slide, how we define these fluctuations. So basically, we write them as a flux difference. And then here, the B tilde, this is this path integral. So we follow the idea of path conservative methods that was introduced by Castro and Perez from Malaga in 2006. So here we just choose the linear segment path. Now I know that in the literature, this is often a point of discussion. Is the segment path good? Well, here actually we don't care, because for the Einstein field equations, we know that all the fields are linearly degenerate. So they cannot develop shocks. So then the choice of the path is actually irrelevant. Yeah, so this is the simplest possible path, right? It's a segment, right? It's rather a simplistic choice. And then now be careful here. This is a Rusanov type or local Laxutix type flux. S max is the maximum eigenvalue at the right. So this is nothing fancy, but be careful. This matrix I tilde here, this is not the true identity matrix, but it's a modified identity matrix, which actually removes the jumps of the equilibrium solution from the numerical flux, because otherwise you would lose the well-balancing property. Yeah. So basically what you need to do is, remember we have this block structure. Q is our actual field of evolution variables, and QE is the known equilibrium. And what we want is that if Q is equal to QE, then the numerical dissipation must disappear. Yes, and we also do not want spurious evolution in the equilibrium variables, which corresponds to the second row here. So we have to remove all the entries here on the diagonal down there. Okay, so you need to modify the identity matrix, and that's it. You could apply this strategy to any problem that has stationary equilibria, right? Just it's a rather general way, but you need to know the equilibrium beforehand. Now, just some words on the predictor. For the predictor, we use space-time basis functions now. Yeah, but be careful, this is just element local, so it's not a fully implicit global space-time DG scheme, which also was studied by Slava and by his colleagues here in Prague. Yeah, so here we just use this as a predictor. So we just solve it element local without taking into account coupling to the neighbors. So what we do, we take our PDE, multiply it with a test function, which is corresponding to these basis functions here, and integrate by parts in time only. This allows us to introduce the initial condition at the known time Tn. Yes, so the WH or UH is actually known. Yeah, WH if it comes from a Wiener reconstruction, UH if it comes from DG. And here, no integration by parts in space. Yeah, we want an element local predictor. We do not want to couple to the neighbors. Yeah, but in principle, what you see here is a space-time discontinuous Galerkin scheme. Now, if you have shocks, of course, you need limiter. And actually, in these Einstein field equations, you have two types of problems. You have shock waves in the Euler part, in the matter part, but you have also singularities in the metric. Yeah, and singularities are even worse than shocks, I would say, right? Because their solution goes to infinity. Yeah, so treating moving singularities on a fixed mesh is actually absolutely non-trivial. And so what we do is, well, we use the a posteriori mood limiter of Raphael Hubert and collaborators. So whenever the DG scheme is too oscillatory, and because it cannot capture right discontinuities and singularities properly, well, then we just throw the DG solution into the trash can, and we use a finite volume scheme. Well, S stands for the stub cells inside each main cell I. U bar is simply the cell average on the subcell. And then we evolve the subcell averages via classical finite volume scheme, but on a subgrid in order to avoid destroying the subcell resolution of the DG scheme, right? I mean, DG scheme may have very high order of accuracy, yes? And then if you have a shock or a singularity, well, you don't want to throw away all the resolution that you have in your finite elements. So you go to a subgrid in order to keep the resolution. Of course, you drop the order. That's clear, right? I mean, you want to deal with shocks. They cannot have high order of accuracy anymore. So you basically, you go to a second or third order Wiener scheme here. And then you want to reconstruct, of course, your DG scheme, your DG degrees of freedom again. So you simply require integral conservation. And with this, from the subgrid, you can come back to the high order polynomials of your DG method. Okay, so just some results. So there are some exact solutions of the equations. Yeah, so it's just a wave that travels over a long, long time, right? The astrophysicists, they like to try testing over very long times to see that your scheme is stable. And these are the errors of the constraints, of this Hamiltonian constraint and of the momentum constraint. So they are very low and they don't explode. So this is nice. Yeah, also for this test case, yeah, this is actually, it's a rather difficult test case for certain formulations of the field equations. So, but here we get a stable evolution. Yeah? So the growth of the errors is linear in time, right? Which is just due to accumulation of round-off errors. Now we can check the convergence of the scheme, and the schemes converge as expected. Yeah, we have exact solutions, so we can compute the experimental order of accuracy. Yeah, this is an interesting test. So this is well. It's called the robust stability test. It's actually a random perturbation of flat Minkowski spacetime. And actually what it is an empirical check of the hyperbolicity of your system. So this is what the astrophysicists do. They take Minkowski spacetime, perturb it, and then let it evolve for a very, very long time and check if the simulation remains stable or not. Well, since we have analyzed the hyperbolicity of the system and we know that it's provably strongly hyperbolic with full set of eigenvectors, well, we know that our simulation should be stable. And it actually is. Yeah, so this is thanks to the hyperbolicity, but it's just a classical test that is done in the community. There is now for the first time we add matter. So this is the accretion of matter onto a black hole. So basically we have a gas that is falling into the black hole. And this is the density profile and the velocity profile. And here we simply compare the well-balanced scheme with the non-well-balanced scheme. And actually the non-well-balanced scheme is not able to reproduce the solution properly, right? It's a rather difficult test case with very rarefied gas, right? Look at the densities here. Yes, so they're very, very small. And in this regime, right, the non-well-balanced scheme does not perform properly. Now, as I told you before, there are many exact solutions of the Einstein field equations that are known. So the most famous one is probably the Schwarzschild solution, yes, of a single black hole. And what we do now is we simulate this Schwarzschild black hole and use the well-balanced scheme. Of course, if we exactly initialize with the exact equilibrium, then nothing will happen in the scheme. The scheme is exact. So you just see nothing, which is too simple. Yeah, so what we do is we perturb the solution, and then you see this here. Yeah, the perturbation is actually not so small, and then during time, the solution settles again back to the equilibrium because waves will travel around. You get a transient solution, and once the waves have left the computational domain, then you are back to the original equilibrium, which is the Schwarzschild solution of the equations. Yeah, we did this in 2 space dimensions, in spherical coordinates. This is in 3 space dimensions, in Cartesian type coordinates. This is just to show you how the solution looks like, the lapse. Yeah, so time is passing slower close to the black hole. Yes, this is the shift vector, and that's just this one component of this extrinsic curvature tensor, which is related to the time derivative of the metric. Yes, and this is just again in 3D how the errors decrease again, and sometimes I'm messing up with the pointer. Yes, so basically what you see, the solution settles back to the equilibrium again. So once we had this, we were actually quite happy. This is a neutron star. So basically here you have the lapse function. So now in the case of neutron stars, the solution is not singular. And singularity is just when you have a black hole. Whereas in the case of matter, then the solution is actually smooth. And you have here the lapse function and the pressure. Yeah? But the problem is, well, it's a compact object, right? So it actually has a finite radius and a finite compact support. And outside it's vacuum. And your code somehow needs to deal with it, right? So if you like Euler equations at low densities, well, you will have fun, right? So this is how it looks like. So it behaved actually quite well. Also, in this case, we actually added a perturbation because otherwise it's too simple. And just to show you, right? Velocity of the equilibrium is of course 0, but since we added a perturbation, it's not 0. It just slowly goes back to the equilibrium. So around 2000, 10 to the minus 6. So. Okay, this is the time evolution of the constraints. And here, actually, in the case of the DG scheme, we did not get stable results with a not well-balanced scheme, whereas with a well-balanced scheme, the simulation was stable. Yeah, so it's still a difficult system to solve. And this is the evolution of the central rest mass density and of the lapse. Yeah, so these results are actually quite good, so because we are able to study small perturbations around the equilibrium. So here, this is a first simulation of a head-on collision of 2 black holes. So you have 2 black holes that are then slowly moving together and merging to a single black hole. And this is the time evolution of the constraints. And here, well, we were able to simulate this up to a final time of 50, and then it exploded again. And then we said, why? I mean, our system is strongly hyperbolic, and I mean, we have used the limiters and everything, and I think we did everything right. And then we were not able to simulate this for a longer time. So basically what we did, we threw everything in the trash can and started again from scratch after 10 years of research and saying, okay, now let's change everything. Let's change everything. Let's change the formulation of the equations and the scheme. Okay, go back to finite difference schemes. So here actually we use central Wiener finite difference schemes, which were invented by Gabriela Pupo, Giovanni Russo, and Doron Levi in 2000. So these are conservative finite difference schemes like those of Shibam Shu and collaborators. So here, this is the flux difference. Then we decided to add these fluctuation terms as in finite volume schemes. So these path conservative jump terms. This is the central part of the finite difference and the source term. Now, how to reconstruct the states and the fluxes? Well, actually, the idea of the C-Wiener reconstruction is the following. You write your optimal polynomial as an auxiliary polynomial, P0, plus a combination of polynomials of lower degree. Here is of degree 2, whereas the reconstruction polynomial has degree n. Okay, taken on a left bias stencil, a central stencil, and a right stencil. Okay, so this is simply a definition, and this definition allows you to compute this auxiliary polynomial P0. It's just an auxiliary tool. The true polynomial that has the optimal degree is this guy here, the P-opt. The advantage of this Wiener approach here, of the C-Wiener approach, is that you are totally free to choose your linear weights. You do not need to compute the optimal weights like in the case of the Zhang and Shu scheme, but you just choose them. So we choose a very large central weight, lambda 0, for the lower order central stencil, also a large weight, and only for the left and right bias stencils, we just take a linear weight of unity. And then the linear weights are combined in this case with the usual oscillation indicator to become the nonlinear weights omega, which are then used in the scheme. Yeah, so what it means in the end of the day is at a shock or at a singularity, the scheme will shift to one-sided reconstructions of lower order, yeah, which is what you see. So piecewise quadratic reconstruction. Whereas in smooth regions, you will use your high order reconstruction, which would be n. Now, there is another formulation of the equations called BSS knock. So actually, we adopted this one. It's a rather widespread formulation of the equations. So it just, we use again all the tools, introducing auxiliary variables, blah, 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 and so on to reduce it to a first order system. All the red terms are actually dirty tricks to make the system hyperbolic. If you don't add them, it's not hyperbolic. Yeah, and these red terms are again zeros. Yeah, so this is something you see them everywhere around. Yeah, if you ask me how we found them, well, intuition and a lot of trial and error. But if you do this, then you can again prove that the system is hyperbolic. You can really compute the eigenvectors. It's almost magic that for such a big system you still can compute all the eigenvectors exactly. So now here we have simulated a single black hole. This solution is also called the trumpet solution. But you see it here, right? This is the lapse function. So it looks like a trumpet a little bit now. And these are the L2 errors of the Hamiltonian constraint and of the momentum constraints. Here you see this stuff is now stable until a final time of 1000. So it's very nice. This is the lapse function, the shift, and this object phi, which actually contains the determinant of the metric tensor. Basically, if you want, there are two tricks in this formulation. You evolve a unit determinant metric tensor, gamma tilde. So this has always unit determinant, and you impose it in each degree of freedom in each time step, and then you evolve the determinant separately. And likewise, the trace of this extrinsic curvature tensor is evolving. Yeah, so this is basically a trick that was used by the physicists. And now, of course, be careful. You have, in principle, a singularity here. So at point 0, this determinant of the metric tensor should tend to infinity. But of course, thanks to numerical dissipation, yes, it's like shock capturing. Thanks to the numerical dissipation, it's actually not tending to infinity, but it's cut off due to the numerical diffusion in your scheme, right? It's but this is an effect of the scheme, but that's good actually. Yeah? This is just a comparison with the standard second order formulation. Here we report the errors, but the errors are reasonably low outside the singularity. So this is far away from the singularity. So this is good. And now we repeat our simulation, this collision of the two black holes. Yes, and now we're able to run this down to the end. Until time 1000, the simulation remains perfectly stable as it should be actually. Yes, so we were very happy when we had these results. And now, of course, what is really generating gravitational waves is the inspiral, and was discovered in the observations in 2015, also experimentally for the first time. Now I will try to show a movie, how this looks like. Let's see if it works. Okay, so here. This is the binary, the merger of these binary black holes. Yeah? So the vectors that you see here are the shift vectors. So this is basically the velocity of the coordinates. Be careful, there's no matter, right? This is vacuum Einstein equations. Right? There's no matter. This is just the velocity of the coordinates. And you get actually a stable long-time simulation of these two black holes, which then merge into a single spinning black hole, a so-called Kerr black hole. Yeah? This is what you get at the end of the day of this process. Now let's see if I can shift back to the talk. Okay, good. Okay, so this is the orbit of the two black holes, and these are the constraints. Yes, and you can run this until large final time in the simulation remains stable. Now, the question that I was asked when I gave this talk last time was, well, now, why does it now work? Is it the scheme or is it the formulation of the PDE? Yeah, because we have decided to change everything, because since it didn't work, in the first attempt, we decided to throw everything away and start from scratch. Well, actually, it's the equations. Yeah, so now we apply the DG scheme again. DG is a little bit fancy, no? And if your system is not robust enough and the formulation is not good enough, then the DG scheme will not work. Yeah, so now with this formulation that I just showed you, this BSS not formulation, we can run single black holes over long times. The formulation. Okay, good. So here there are some references. Yeah, so I hope I'm more or less on time. And so thanks for inviting me here to Prague. And if you have questions.
Thank you very much for a very interesting